All right, today we are finally going to finish off the introductory session of the Xanadu Quantum Codebook, which means that we can finally do some more interesting works with Penny Lane. And I can complain some more. Hopefully no developers are watching and taking this personally. I complain a lot about everything, so not personal. So here, yeah, we're just getting right into it. You know, this is a more free form. You want to go back and start the series anew. That's good, but it's more free form, less planned than other sort of discussions. So yeah, we got some bell states here. So what are we doing? Implement each of the bell states. Okay, I don't want to, but I will. Every single one of the bell states starts with a Hadamard on the first qubit. And every single one of them, you can do a C0, 0, 1. This is the standard one, so that's it. This has a Z gate, right? Because we're flipping the phase, not poly Z. This has a X gate, right? Because you can see they're offset. And this has an X and a Z gate because they are flipped and the phase is off. All right, that should be correct. Really hope that's correct. And it's not correct. I should print the results. I probably made a simple mistake in my reading of the code. Okay, 0, 0. Oh, I see. That is my bad. Whoopsies. I simply forgot that they should be after the C0 operation. You can see them here. Right, they should just be after the C0. I've mistyped them. All right, let's speed run this. All right. Implement a 3-qubit circuit. If the first qubits do nothing, if the first qubit all right, multiplexer. Well, let's do this. Let's just follow what their comments say. If the state of the first qubits is 0, 1, apply the X gate to the third qubit. How do I do controlled operations? Oh, they're over here. But it doesn't tell me what their Penny Lane references are. Very, very, very fun. Of course not. Why would it tell me that? So what we're going to do is look up Penny Lane controlled operations. Quantum operations, identity, don't care about parametric. I want to sort of there's really not. See, that's the nice thing about Qiskit is they have sort of arbitrary controlled operators. All right, I'll just do this. If the state of the first 2 qubits is, all right, so we want to do, oh wait, this is QML dot poly x 0 QML dot poly Myers equals 0, 1. 2. Then we want to uncompute what we just did, right? All right. Okay, if the state of the first two qubits is 1, 0, apply to z to the third qubit. Okay. This would be easy if I could do a multi-controlled Z gate, right? But I just have CZ. So what we can do is we can do QML.CZ wires equals 0, 2, and then QML.CZ wires equals 1, 2, because if it's 1, this will trigger, and if it's 0, this will trigger. This won't trigger, which will uncompute it, but that would also be true for 0, 1. Huh. So what we can do is we can add a X gate and do this again. Oh, but that's not what we want. If it's in the true state, it's in the false state, that won't do anything. Let's see, so if it's in 1, 0, this one goes off. This one goes off, this one does nothing. If it's in the state 1, 1, this one goes off, this one undoes it. If it's in the state 0, 0, nothing happens. If it's in the state 0, 1, this one doesn't go off, this one does go off. Okay, so we can just actually apply this twice, right? So we can say 1, 0, this goes off, these two do nothing. 0, 1, this one doesn't go off, these two both go off, undoes it. 1, 1, this one goes off, and this one goes off. These two cancel. Oh my god. Oh, why am I trying to do this? I'll just do it the easy way. So what I can do is poly x to wires 1. Now we're gonna switch bases. Oopsies, we need to switch bases before doing that. Now we can simply uncompute. Okay, now we want to do the same thing down here, but switch it to the Y basis, which I don't remember how to get to the Y basis. I remember it's in one of these previous ones. Oh, right. Hadamard and S. That's what it is. All right. Let's see if this is right. Okay. Does not have the correct action. All right. This state is 0, 1. Let's try 1, 0. All right. So this is 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Oh my god, I need a stupid sketch pad for this. It's a real shame that there's no state vector. That's the nice thing about Qiskit. It has a state vector. Okay, so we have 0, 0, 0, comma 0, 0, 1, comma 0, 1, 0, comma 0, 1, 1, comma 1, 0, 0, comma 1, 0, 1, comma 1, 1, 0, comma 1, 1, 1. So the states we care about, right? Because we're inputting 1, 0. We care about these two. So it should be 1, 0, 0. And this is in a superposition. The default is 1, 0, 0, 1, 0, 1. All right. So if we apply the controlled Z gate, we would flip this sign, so it should be plus. Okay, where is a complex number coming from? Because that does not make... Oh, there's no complex rotations. What the hell? What is going on here? Oh, I see. I see what's going on. I'm doing all these operations sort of in sequence, which is confusing me. So let me see what happens if I just do this. Focus on the one we care about. So we get plus and plus. Okay, that's right. So now let's add this back in. All right, that's right. So now we need to consider 1, 1. Okay, the question is, why did I add a polyx here? I think that's what's messing me up. They're 1, 1 state, so it's already there. All right, let's see if this... Okay, there we go. That was just a typo that was messing me up. All right. There's sort of multi-controlled operations that are very annoying to do if you can't just specify them like you can in Qiskit. All right, moving on. All right, quantum teleportation. I can't remember if I've done a video on this before. I feel like, I don't know if I explicitly did it, but it was like in one of them. But that's unimportant because now we are pick your favorite single. Okay, pick your favorite. I'll leave it as theirs. That's fine. We will now teleport to state. No, I do not need to do that. Okay. That's my favorite state, I guess. Entangle. Oh, so we're doing it step by step. So we want to do Hadamard on wires equal 1. And then we want to do, we're creating the bell state here equals 0, 1. So we're just making the bell state here, which is this little blue box. Okay, am I supposed to return it? Oh, oopsies, this is 1, 2, not 0, 1. All right, change of basis. So we have our xenon on the first two. This is the little green box, turquoise. And then our Hadamard, once again, annoying that I can't type H. On our first qubit, now we have our controlled operations and measurement, I assume. So we do qml.c not wires equals 1, 2. Then we do qml.cz wires equals 0, 2. There we go. Now we just have to use our functions here. We have our state preparation. Then we do entangle qubits. We do rotate and controls, and then we return qml.state. Oh, it's not it's a lowercase function. I was like, this is awkward. No, it's lowercase. There we go. Look at that. We copied the state. But it's not, once again, this would be really easy if I could manipulate things with some sort of state vector class, but there isn't. So we have to do more work. You can look through here. I really feel like I've gone through this before, but you can look through here if you want to. If you want to figure out exactly what's going on, if you don't know what the state preparation is. With this knowledge, write a function that takes the state vector and outputs the state. All right, so it's a factorable state, right? So we just care about this. The A plus B. So what that means is we have A is going to be every other one, right? So we have, let's see, A equals I4 in range 0, 8, 2. And then we have, let's see if this is, I'm trying to be clever right here. So let's see, 1, 8, 2. And so then what we can do is we can say, so it's going to be, oh, I don't even need to be clever. I can just look at the first one. We can say return, right? Because it's return numpy.array of 2 times input state 0, 2 times input state 1, because this is, remember, right? So if we're doing FOIL and, multiplying this all out, I was going to be clever, but that's all we need to do, right? Because we have this amplitude times 1/2 for the first one, this amplitude times 1/2 for that one. times this one. So the first two states are all that we care about. All right, we have finished introductions. I think next we're going to go into basic quantum algorithms. But that's all for today.